Welcome differential equation fans, video on Laplace transforms and the impulse response. So in this video we'll motivate our discussion with the physical system. We'll have a look at Laplace transform approach to solving the system using the convolution. We'll see how our initial intuition about an external force fails. We'll patch that up with a better description of the external force and see how that better description can be used in context of a Laplace transform. We'll close with a discussion of a couple input-output systems. So here's a physical system. Physical system is a particle moving along a line that experiences two forces. So one force is a damping force proportional to its velocity, and the second force is some external force. So we'll assume that this particle has a zero initial velocity. So with that information, we can drive an initial value problem for it, and we'll go ahead and just use Newton's second law here that says the mass times acceleration is the sum of the forces. And in this case, the mass times acceleration we'll take to be the mass times the velocity, and for the sum of the forces, we'll take those to be the sum of this resistive force and the external force. So an ODE for the velocity is mv prime is minus rv plus this external force that we're just calling f of t. Okay, so together with that information about the initial condition, v of 0 is 0, we have a perfectly good initial value problem for which we can identify the Laplace transform, solve for the transform solution here, and go ahead and write the velocity therefore as a convolution, right? This transform 1 over s plus r over m is just the transform of e to the t. It's actually e to the minus r over mt instead. In any case, the convolution theorem gives us the solution, which is the integral of this exponential times the forcing function. Okay, so now let's think a little bit more critically about the forcing function, and let's assume that we have a special type of applied force that's an impulse that acts for only a single instant of time. So we can sort of think of this as a force maybe that just has some non-zero value at some time 0 and some time a and is 0 otherwise. So this would be the force. Our intuition tells us that adding this force, which is a change in mass times acceleration, should go ahead and get this system started. Of course, if there's 0 velocity at time 0, we're going to see that nothing happens, but this force at point A should get things going. We'll call this little f of t. Okay. So perhaps we can just express this impulsive force as something that's 0 for all t not equal to a and non-zero for all t equal to a. And if we go ahead and use this force in our integral, it turns out that we get something that doesn't match our intuition. So what we get if we use this in our integral is v equals 0. It turns out, again, just plugging this force that's 0 almost everywhere into this integral gives us a v that's not 0. Okay, this is not what we expect. Something went wrong, and it turns out what went wrong is our interpretation of this impulsive force. So to have a better look at that, we'll go ahead and think instead about this idealized force. So I'll define a function f sub epsilon comma a of t to be the impulsive force centered at a with width epsilon. Okay, so here we see a graph of that force, and again, this width on which the force has a non-zero amplitude is width epsilon, and you can see its height is 1 over epsilon. So certainly we can identify the area under the curve here. The area under the curve is just the area of the corresponding rectangle, and that area is 1. Okay, this is a pretty cool thing. This idealized force has area 1. Okay, so now we'll go ahead and define this new function, this delta function, to be the limit as this idealized force goes to 0. So you can imagine that as epsilon gets smaller and smaller, right, this width gets smaller and smaller, but the height gets taller and taller. Okay, and it turns out that in the limit as epsilon goes to 0, we get something that ends up being what we wanted, namely something that's non-zero for all t not equal to a, non-zero for t equal to a and 0 for t not equal to a. Okay, and we'll take it to have the property that the integral, the area under the curve from 0 to infinity is always 1. Okay, so it turns out that this function is not a function at all. It's called the delta function. It's referred to as a delta function. Real functions don't have this property, so instead we sort of think of it as a class of idealized functions for which they're characterized by their value under an integral. So as you might expect, this sort of adding 1 to the force ends up being sort of a step increase in momentum. Okay, and it's this function that actually has the property that we want. The delta function is defined by this so-called sifting property, namely that if we integrate this delta function against any function phi, here we just pick up the value of phi at the place where this delta function is activated. So we can do something a little bit different, and instead of integrating on the interval from 0 to infinity, integrate on the integral from 0 to t instead. And the value of the resulting integral depends whether we've crossed that threshold where we've activated the delta function. Of course, we'll get 0 if t is less than a, and we'll get phi of a if t is greater than or equal to a. And this should remind you of something, right? This should remind you of some sort of heaviside action. Okay, so this ends up being represented by the heaviside function as phi of a times heaviside of t minus a. Okay, so we can rewrite that actually in other terms too. So this is the way we first saw it just a moment ago, and if we translate tau here, we can translate similarly in phi of t minus tau, and this should remind you a lot of a convolution, right? So this last one looks exactly like the convolution of phi with the delta function. Okay, and it's that property that's going to be exactly what we need. Okay, so that convolution ends up being h of t minus a times phi of t minus a, this switching property. Okay, so let's see how this works for our idealized force. If we use this delta, the sifting property with the cosine, right? Again, here we're just going to pick up the value of this function phi. Here I'm thinking of the cosine playing the role of phi. We'll pick up this value of phi at 1, and the value of phi at 1 is just cosine of pi over 4, which is equal to the square root of 2 over 2. Now the sifting property works also on our model problem. So if we think about integrating this exponential against our idealized function here, again, we're going to get back exactly the heaviside function at t minus a times this exponential at t minus a. Okay, so here's a convolution, and there should be a t in here, of course. Sorry about that. And when you write this out, you get exactly this thing switched on at t equals a. So go ahead and graph this. You see what you would expect, namely that things activate here at time a with some amplitude that's 1 over m, and things then decay away according to that force. Okay, so this is exactly the impulse response that we expect, that up into that time when we employ this impulsive force, things remain zero. We get a jump discontinuity in the velocity, again due to the change in momentum, and by changing that momentum, our velocity then decays away exponentially. Okay. So let's go ahead and talk about the Laplace transform of this delta function, and there are two ways we're going to look at it. The first way is to think of this unit impulse centered at A as a sum of Heaviside functions. So if you want to think of the unit impulse centered at A as a sum of Heaviside functions, you can do that. After all, it's just a square wave centered at A that turns on and off here at A minus epsilon over 2 and A plus epsilon over 2. Okay, so that Heaviside function sum looks like this, right? It's oh, by the way, this is at height 1 over epsilon, right? So the first thing that happens is this one turns on. The second thing that happens is this one turns this off. And you can go ahead and look at the Laplace transform of this idealized force by looking at the Laplace transform of the two Heaviside functions. So I'll encourage you just to verify this. It turns out to be convenient to write this in terms of the hyperbolic sign that we see here. And when you do that, we can think of the Laplace transform of the delta function as the limit as epsilon goes to 0 of the Laplace transform of this idealized force. So I'll have you verify this part 2. That when you take the limit as epsilon goes to 0 of this thing right here, what you end up with is just e to the minus as. And there's a L'Hopital rule to be done in there, but it's not a terrible calculation. Okay, an alternate way to think about the Laplace transform of the delta function is just by using the sifting property. So here's just the definition of that Laplace transform. The definition of Laplace transform of anything is the integral of that thing against our kernel. And when you go ahead and think about that sifting property, namely that we pick up the value of this function here, I'm calling this function phi of t at t equals a, what you end up with is exactly e to the minus as. Okay, so in either case, the Laplace transform centered at of the delta function centered at A is e to the minus as. Now something interesting happens here if you think about the Laplace transform of this unit impulse or delta function centered at 0, namely that you get the Laplace transform as 1. Now I'll remind you of something we talked about in our introduction to Laplace transforms, which is that the Laplace transform of all nice functions has the property that it goes to 0 as s goes to infinity. Now certainly 1 doesn't go to 0 as s goes to infinity, which means that our delta function is not a quote-unquote nice function. Okay, so certainly functions that act like this are not nice functions. They're not piecewise continuous and of exponential order. But it does have a Laplace transform, and in this case the Laplace transform again of delta sub 0 happens to be 1. Okay, so here's an example of just an initial value problem not motivated by a physical system that we can use the Laplace transform to solve. So we'll start off by transforming the initial value problem, again by just transforming the left and right hand sides of the differential equation. Okay, so here's the transform of the left hand side, the transform of the right hand side. Those must be equal, which allows us to solve quickly for the transform solution here, x of s. Okay, so this transform solution sort of has three components. One component is this 1 over s plus 3. There's a component involving e to the minus s, and there's a component involving this e to the minus 4s. So we'll go ahead, and by the way, I've used a partial fraction decomposition here to take apart our rational function. Okay, so we can use the inverse transform to find the solution, and here are those three parts again, right? The three parts are the part involving e to the minus st, the part involving this first Heaviside function, and the part involving the second Heaviside function. And you can sort of think about those three parts modularly in a module fashion, right? So here is our initial value problem starting at 1. When we start at 1, the first thing that happens is that this delta function hasn't done anything, and this Heaviside function hasn't done anything. So in this area, we're just looking at x prime equals minus 3x, and our solution just decays. Now the next interesting thing that happens is at time 1, we employ this impulsive force, and we can see a jump in the solution, a unit jump in the solution accordingly. Okay, after that happens, things are going to just decay away again like they did before. In here also, we satisfy the differential equation, x prime equals negative 3x. Okay, we satisfy that differential equation until time 4, when we switch on a Heaviside function, and at time 4, things look like x prime equals negative 3x plus 1, which we expect to equilibrate to 1/3, and it does that pretty quickly. Okay, so again, the Laplace transform takes care of matching up these domains, and you can see sort of this this impulsive or this jump discontinuity due to the impulsive force. Okay, a second example is this one, a second order equation that has some impulsive forces. X double prime plus 4x is delta sub 2 of t plus delta sub 10 of t, with x of 0 equals x prime of 0 equals 0. So as usual, when we look at a second order differential equation, we'll think of this as some sort of mass spring system here. We can think of this as an unforced mass spring system, where an undamped mass spring system, where there are two forces that come into play at time 2 and time 10. Now, of course, the initial conditions are 0 initial velocity and 0 initial position. So we can use the Laplace transform to, again, transform the initial value problem, transform in the left and right hand side. So here's the transform solution. That transform solution, again, is just by setting these two equal and solving for our transform solution. Okay, so there's a component here involving e to the minus 2s and s squared plus 4, a component involving e to the minus 10s and s squared plus 4, and we'll go ahead and use the inverse transform here to represent the solution using our switching property. So we can see here a switch on at time 2 and a switch on at time 10. So when you go ahead and graph this, it has just the behavior that you think, right? Initially things are 0. An undamped, unforced system at rest is nothing's going to happen. We add an impulse and things start oscillating. Okay, things start oscillating until this time 10 when they're on the way down, and we give it another little kick up, at which case they oscillate a little bit slower. Okay, so again, pretty cool use of Laplace transform to connect up all those discontinuities, and again, what we're doing here is just applying a unit force to the acceleration, right, which we see as we see in the change of momentum here, instantaneous change of momentum. Okay, so finally close up this system with a brief discussion of input-output systems. So in general, we've been looking at this differential equation, ax double prime plus bx prime plus cx is f of t. And here we have so-called rest conditions, or 0 initial position velocity. You can think of this as an input-output system, and if you have a look at the Laplace transform, you can cook up the solution by transforming both the left and right hand side. You can imagine that you get something like aas squared plus bs plus c all times x of s is f of s, giving us that the solution here is just 1 over this polynomial, this quadratic, times f of s. Okay, so we're going to call k of s the transfer function, is sort of what transfers the system to the solution. Okay, so to see that transfer function in action here, we can see that in this second order differential equation where there's some sort of impulse at time a, we can solve quickly, And we can think of this as, again, some sort of transfer function here, k of s times f of s, where f of s represents the Laplace transform of this impulsive force. Okay, so complete the square appropriately, and we can do a little bit of multiplying and dividing by 2 as usual to see that this looks exactly like the transform of some sort of decaying exponential times a sine function times e to the minus as. Okay, so the solution ends up being the convolution of those two guys that we can see. Again, the result here is just the Heaviside function. Okay. So to graph that, when a is equal to 2, we get exactly the impulse response we expect, namely that nothing is going on until a equals 2, until we give the system a crack with our delta function. It gets going and it decays away like some sort of damped oscillation. Okay, folks, that's it for discussion of impulse functions, Laplace transform of the delta function, input-output system. So hope you've enjoyed this video. We'll see you soon. So long for now.